All right, so it just happened. Okay.
I should have noticed. Thanks, Zach.
Zach's on top of it.
Yeah, slacking.
It's like, I've had a lot of classes, there's somebody behind the camera who will notice it, but I have another class where no one ever notices it.
I was behind it in our other room and I never even looked at it, so.
Yeah, all you need is one person.
You just need one attentive person who's really locked in.
We're distracted from the lecture.
No, I just have good peripheral.
So to clarify, what we just did here then, is this considered incorrect because we have not accounted for the change in mass?
Correct.
So this is wrong.
This is wrong because
This makes
this,
sense.
that 3 kilogram mass question is what, typically you're given the rest mass. This would be the rest mass is 3 kilograms. I was very vague on that purposefully. But the actual mass here is not 3 kilograms.
Right, it would be 3 kilograms times gamma.
Right.
Right.
Right. Or for others in the physics world, they'd say, well, it's not the mass that changes, it's the momentum that changes by gamma. You're gonna multiply gamma in here either way. So anyway, that's the justification. A little bit more specific than what I did on Friday. All right, other questions?
If on an exam we get a question like this and we do this because we forgot whatever the other part was, is this worth something even though it's wrong?
It's worth something, yes. I mean, you do have the relativistic time, the relativistic velocity changes.
Right.
If you just treat it like a 151 problem, then no, where all this stuff goes away.
Right.
I get, maybe there's a sympathy point for remembering how to do a momentum problem, but. All right, about to do an awkward transition.
It's never a good time. Just do it.
All right, and the last thing is I think I wrote up the Doppler shift equation on Wednesday at some point in the past. I guess when in the past, depends upon your reference. I want to actually derive it. Some planet that begins with the letter E. A rocket heading towards it. The rocket is going to send out a signal at some regular interval. There'll be some regular period. In other words, there'll be some set time. So like once a second, it's going to send out a signal, or once a year, whatever, some signal. So it lets out a first signal here, and that signal starts moving at the speed of light. Because it's traveling through a vacuum, it better be an electromagnetic signal, otherwise it would never make it. I guess they could shoot particles. So after some time later, this first signal is now here, has gotten this far, and the rocket is now here. And it sends out the second signal, which is now going to also be traveling at the speed of light. So basically, it sends out the first signal, then that first signal is now here. I guess if I'm doing cartoon panels here, that's the first signal, that's the second signal. So the wavelength that the Earth is going to receive is just basically, that's the distance right there. That is the wavelength that the Earth will see. Because that first pulse is going to hit it, and then just a short time later, or in some time interval later, it's going to hit the second one.
Wait, could you clarify that piece one more time? I missed it.
All right, so the rocket ship sends out a signal, beep, and then sends out a second signal, beep.
Yeah.
And so those two signals are now traveling with each other at the exact same speed.
Yeah.
And they're going to hit Earth. And so Earth is going to see the first signal, it'll see the second signal, and the distance between them is the wavelength, just like the peak of two waves.
Huh, okay. So the signal is not like a 600 nanometer signal. It's like a little blip, and then the other part of the signal is the other blip.
I'm not specifying I'm not specifying the frequency or the wavelength, it's just something. It could be 600 nanometers, or it could be 6 meters or 600 meters.
So the wavelength is just the distance between the blips.
Yep. If you want to think of it as it's sending out a color, some frequency of light, that works as well.
I'm truthfully trying to find an application for the assignment that we have to finish today, because there's a question that's very similar to this.
Okay.
So, efficient.
Now, so the wavelength from Earth's point of view is going to be, well, that distance right there, that's how far the first signal went, and that distance right there, how far the rocket went. So it's going to be the speed of light times how much time it took between the signals, which is some period from Earth. Again, this is all from Earth's point of view, minus the speed of the rocket times however much time was between the signals, again, from Earth's point of view. So that's equal to c minus the speed of the rocket times the amount of time that elapsed between them, the period. Period is how long it takes to produce a signal, and it produces a signal once every year, once every second, once every whatever. Now, questions up to here? And by the way, deriving the Doppler shift for sound is very similar, except the fact that time is the same in both cases, because we're not dealing with relativistic sound. That'd be quite the sonic boom if you got a sound traveling that fast. Anyway, so in deriving the Doppler shift for sound, you just are losing this bit. And c would represent the speed of sound. All right, so now let's bring in the fact that we're dealing with special relativity. We have two different times involved here. We have time on Earth, and we have time in the rocket. The rocket's the one traveling really fast from Earth's point of view. Earth's not moving. And so we have the time on Earth is equal to gamma times the time on the rocket. Time dilation, this would be, in essence, the first formula we derived. So I'm going to make that little substitution there. So c minus VR times gamma times the time on the period on the rocket, from the rocket's point of view.
Can I ask you a question about proper frames?
Yes?
So when we did the example about the box of whatever it was, and there was a mountain involved, and we were talking about which one of these is the proper frame.
Right.
We had determined that the actual height of the mountain was the proper frame.
Right, because when measuring the length of the rocket, mountain, one of those two syllable words.
Right.
When measuring the height or length of the mountain,
Right.
the mountain is at rest relative to the people on Earth.
Yes.
Relative to muons, the mountain is not at rest.
Which is why I thought we had concluded that the proper frame was relative to, like, my paraphrase is like what actually exists, which I know is not the case, but that is how my brain is wrapping my head around it.
Okay.
And so with that logic, it seems like everything should be relative. The proper frame should always be relative to the Earth, and anything that's being stretched or manipulated is not the proper frame. But every single example we've done since then, we've always done like the rocket ship moving at some fraction of the speed of light as the proper frame. So I guess I'm just confused about how we can determine which is the proper frame in a problem. Because everything gets flipped backwards if we get that wrong.
Yes, that's true. Well, if you end up with a gamma less than 1, then you've got it backwards. I mean, not trying to be flippant, I mean, that actually is
That makes sense.
a legitimate strategy here.
Right.
So I'm talking about how much time passes on the rocket, the time that passes on a rocket, so people in the rocket looking at a clock, that time that passes from their point of view is the proper frame, because that time is at rest relative to them, or the measuring instrument's at rest. And Earth would not be the proper frame. if I was talking about on Earth here, someone's looking at a clock, then what they're seeing is a proper frame, and from the rocket's point of view, it's moving. But from the rocket's point of view, frame that Earth's zipping towards it.
So it always depends on the question.
Yes, it does, very much.
Thanks.
Now, so in this particular example, I established we're doing this from the Earth's point of view, and now I'm bringing the rocket's point of view into it. Because I know that the time on the rocket relative to Earth is not going to be as much. Is that sufficient for now?
Okay.
Okay. All right, so go back to waves. This is stuff that we did near the end of 151, or actually presumably for even those who didn't have me, at the end of whatever 151 class you were taking. The fact that if I'm dealing with a wave, I know that speed is equal to distance over time. I guess we did this the other day also. And if I have a wave that's being produced, then the distance it travels in a time, in a period, is just equal to the wavelength. And period and frequency are reciprocals, and so speed is equal to wavelength times frequency, or frequency times wavelength. In other words, period and frequency are reciprocals of each other, so this is just C minus VR times 1 over the square root of 1 minus, what's called beta squared, times 1 over the frequency from the rocket's point of view. And that's equal to the wavelength from the Earth's point of view, which would be, looking at our equation over there, that the wavelength is just the speed of the wave divided by the frequency of the wave. Looking at this right here, V is equal to lambda F, and therefore lambda is the speed divided by the frequency. It's the speed of the wave, that's why it's C. So what I'm going to do is I'm going to divide both sides by C. So times 1 over C and times 1 over C. That's I'm going to distribute that through here, and so what I'm left with is 1 minus the speed of the rocket over C, which is just beta, divided by the square root of 1 minus beta squared, times 1 over frequency of the rocket is equal to 1 over frequency of, from Earth's point of view. I guess frequency of the rocket is misworded. It's the frequency that the rocket feels like it's producing. Now this is not the typical form for it. I have 1 minus beta here, so let's go ahead and do a little fancy math. So that is the square root of 1 minus beta times 1 minus beta. And down here, how do you factor this? Algebra problem. How do you factor 1 minus beta squared?
Isn't it just 1 minus beta?
Yes,
Well, that whole
it should be
thing
just
should be
1 minus
one
beta,
minus
right?
It is not,
Oh, right, because only beta is squared there.
correct? Well, 1 squared also, but
Oh, it is. It's 1 minus beta squared.
no. It's 1 squared minus beta squared. Does that make you feel better? It's still not 1 minus beta is the final answer. That doesn't work that way.
No, actually, that confused me more. Because down here you don't have it squared.
How do you factor a squared minus b squared?
Square root it?
Factoring.
Factor
Oh,
it.
yeah, you
Wait,
just take
is that
out
just
the,
a times a minus b times b? I don't know what you mean by factoring this. I'm sorry.
If I had, so the opposite of factoring is foiling. This is sort of the reverse FOIL.
could you take the square out?
Well, it depends on what you do with it after you take the square out.
It's a good idea though. Whatever it was. factoring and foiling have always been hard for me.
Hang on. Wait a second.
Genius is coming.
This is really Zach's expertise. This is, I just from
Yeah, you're
working.
so silent.
Isn't
You're
it
so
just
working
silent.
with him?
Is it- so we should
A
hold on
minus
until
B?
Zach tells us?
He,
Yes.
well, I'm going to figure it. I'm going to try and figure it. But and whenever I work with Zach, this is where I go to him to help me. I need to.
Yeah, I'm not sure exactly what's being asked, that's what I'm not speaking of.
Okay, so let's.
Alright, so-
Foiling is the inside-outside thing.
If I had,
It should be expanding, it would be factoring.
x squared minus 2x plus 1, I would factor it into x minus 1 times x minus 1.
Yeah, that's always.
That's factored when you go from this way to that way.
Right.
X squared minus 3x minus 2, that's probably not a good one to do. Minus 4 would be x minus 4, x plus 1.
Yeah, I can have it again. So what you're looking for is a couple of different sets of parentheses here. Yep.
Yeah. Just trying to go through it.
Okay, so we need an A in each of them and a B in each of them to get them to be squared. So A minus B, A plus B is my guess?
Yes.
Nice.
Oh, that's what I had.
I know it is.
God.
You got it before me. All the credit's yours.
So the one is a perfect square there, I don't have to actually write square, 1 is squared already, so this is 1 minus beta, 1 plus beta, times 1 over the frequency from the rocket's point of view. And so now we got some canceling out that we can do, we got a 1 minus square root of 1 minus beta and a square root of 1 minus beta. And so what I'm left with, after all of this, is a need to erase. So 1 over the frequency from the rocket's point of view, Earth's point of view, is 1 over the frequency from the rocket's point of view times the square root of 1 minus beta over 1 plus beta. Or, the more traditionally, they take the reciprocal of it and you get the frequency from the Earth's point of view. The frequency of the receiver is equal to the frequency of the sender times the square root of 1 plus beta over 1 minus beta. And that's the equation that I gave you the other day. So, the equations that I gave you was more than just stuff I made up.
I just blindly trust, regardless. But thank you.
I didn't want you to wake up in the middle of the night screaming, how do I know any of that's true?
True. Yep. Like, was this all a lie? Like, I don't know. Did I spend this whole semester and
Year.
year?
And, it could be, it's all modeling based upon assumptions. It just disproves one of the assumptions and boom, you'll be reviled and revered all at the same time.
That's all I want. I want to be revered.
You have to do both. You can't have one without the other.
No, I just want to be revered.
Now, the whole idea that particles can't travel fast, particles that start slower than the speed of light, or can't travel faster than the speed of light, in about 10 years ago, there was some evidence that they actually managed to get a particle traveling faster than the speed of light. And so they're trying to figure out that that can't be right, because there's so much evidence to support all of this stuff. So where did it go wrong? And they did a very thorough investigation. One physicist said, I don't know if there's a mistake anywhere, but that's the most thorough investigation ever done, because they were taking into account the warping of space because of the mass of the Earth, and they were taking everything into account. Also, the actual mass layers of the Earth right there where their experiment was done, not just treating the Earth as one homogeneous body. And they eventually did find the mistake. There was one faulty piece of equipment. And we're talking billion-dollar equipment here, multi-million-dollar equipment, and there was one tiny little bit that was off.
So in our universe, speed of light is the fastest. Like, what about black holes and stuff? Like, is that just not that we know of, or?
If you Let's talk about black holes for a second.
Okay.
Do I have to look here or do I have it at home?
That's okay.
Stupid pandemic jerk face. All right. It was one of those thick cardboard books. If you ever read books to small children, the books designed for them to hold. It's really thick cardboard. So this was a book like that. It was, you know, a big book, but thick cardboard. So, you know, a children's book. And it was a story of this guy who's sort of a hotshot. He flies near the edge of a black hole and then comes back. And then after he's finished doing that a couple times, he comes back and he radios back to the mothership and says, "Hey, do you read me?" And there was no answer. I mean, that's basically, you got this big piece of page, lots of colors, except for the black hole right there. And it said, and no one answered. Kid's book.
Nice.
It turns out everyone he knew was dead.
Wow.
Oh, no.
Yeah.
You should read it to us on Friday before our final.
Get us ready for it.
The student who gave it to me said that she got it because it was a kid's book, she thought. And then she said, it freaked me out. It turns out, as you get near the edge of a black hole, not only does speed change time, but the warping of space causes a change of time also, which is what a black hole does. And so everyone else had died of old age by the time he'd come out of it. He did not age as much. So, yeah, lovely children's stories.
Nice.
So that's right, you talked about, what about black holes? Black holes are still not traveling faster than the speed of light,
Okay.
but you do get a distortion effect from it of time.
Cool.
Or of space-time, actually.
Space-time. Nice.
All right. Now, there is a theoretical particle that does travel faster than the speed of light. It just can never go slower than the speed of light. And that's the tachyon.
The tachyon.
Tachyon.
Which big letter is that?
I've only seen the word spelled out. I haven't actually seen it symbolized by a smaller thing. It's theoretical. It's, again, the theorists going, well,